All right, now we're going to talk about acceleration, which is a vector. So the acceleration vector. So here's a question. This is a very important question. Pause your video and answer it. And let me just give you a hint. So delta t, here's delta t. Now delta t is t final minus t initial. Well, you know, that's always going to be positive, right? We don't go back in time, sorry. So delta t will always be positive. So that's a huge hint. Here's another hint. The direction means the sign, agree? So if something is going that way, it has a positive sign, like velocity, right? If something's going that way, it has a negative sign. So there's two big hints, so pause your video and figure it out. All right, the answer is the same. Why? Well, kind of like what I just said. So A average equals delta V over delta T. Now, delta T is always going to be positive. So doesn't that mean that this sign has to be that sign, right? If this is negative, doesn't that have to be negative? If this is positive, doesn't that have to be positive? Well, yeah, because this is always positive. And so if this is negative, points to the left. That means this points to the left. This is positive, points to the right. That means this points to the right. That's all there is to it. Okay. So here's why we care. This is why we care. So this is what we're saying. We're saying the direction of A is the direction of delta V. Not the magnitude, right? Just the direction. All right, now, what does delta V mean? Delta V means V final minus V initial. So that's all there is to it. So you see, I made the magnitudes different on purpose, right? But they have the same direction. So the direction of A is the direction of delta V, which is the direction of V final minus V initial. That's incredibly important. And that's why we learn to subtract vectors, because oftentimes we want to figure out the direction of A. And it's a vector subtraction, right? The direction of A is the direction of V final minus V initial. So that's what I mean. You have to know how to subtract vectors to do that. All right, you've seen this before in a previous chapter, but I didn't explain it back then with vector subtraction because we hadn't learned vector subtraction. But now let's do it with vector subtraction. So I want to figure out the direction of A, right? That's all I care about, the direction of A. All right, so the direction of A is the direction of V final minus V initial. So this is V initial, and this is V final, right? So let's do it. So I want V final minus V initial. Well, again, vector subtraction. That's V final plus minus V initial. So let's do it. Okay, so V final is this little guy. So there's V final. And then, so that's V final. Okay, now, I'm not going to draw it on top of it because you can't, it's too hard to see, right? So that's V final. And then minus V, okay, so here's V initial. So minus V initial, you know, head to tail is kind of like that, okay, minus V initial. So you go from beginning to the end, and there's your delta V, okay, which points to the left, which is exactly what we said. All right. Let's do another one. Okay, we did this one as well. Okay, so look at it. So this one, the velocity, the object was going this way, right? Now this one, the object is going this way. So let's just do it. Okay, so this one, you know, we're starting here, and we're going that way. So that's V initial, that's V final. So, okay, so V final is this guy. That's V final. And then minus V initial, that short guy that way. Again, I'm not going to draw on top of it. That's minus V initial. So same thing, right? So you go from the beginning to the end. So there is delta V. Okay, which points to the left. So there you go. Okay. So you're going to see soon enough that we'll use this quite a lot. So last semester in a different class, we had learned how to do vector subtraction, and then I don't know, it was like the next class or maybe the 2 classes later or something like that. We were going over this direction business, and I was explaining it to people. And a lot of the kids, not a lot, some of the kids in the class raised their hand and they didn't understand how to do vector subtraction. And I was really irritated. Hopefully I didn't express that, but I was really irritated because of what it indicated to me was that they hadn't even bothered learning what they were supposed to have learned like 1 or 2 lectures ago. So don't do that. Keep up. So anyway, there you go. All right, let's see. Now, we just did this, right? Like 15 minutes ago or something like that. So let's do it again. So this is actually, this is uniform circular motion. What does that mean? It just means constant speed. So I mean, this is supposed to be a perfect circle, but it's not. So, but just pretend it's a perfect circle. So it's circular motion, but it's constant speed. So it's kind of like, so it's like this. So I'm going in a circle, but my speed is constant. All right. Now, so an object undergoes uniform circular motion as shown. So is the object accelerating at point A? So pause your video and answer it. All right, let's get back. So what's happening at point A? What's happening everywhere in a circle? Remember, the speed is constant, but what's happening to the direction? It's changing. Well, acceleration is the change in velocity over the change in time. Velocity is speed and direction. So if the direction is changing, it's accelerating. So the answer is yes. And because the direction is changing. Okay, so that was a review question. You should know that. All right, now what I want you to do, and make sure you do it on a piece of paper, and do it well, you already did it, but do it again, it won't hurt you. An object undergoes uniform circular motion. Use vector subtraction to find the direction of the acceleration at point A. So what am I talking about? How can you find the acceleration, the direction of the acceleration vector at point A? Well, go back to this. The direction of the acceleration vector is the direction of delta V. That's the direction of V final minus V initial. Now, let me change this just a little bit. Instead of saying V final and V initial, I'm going to say V after and V before. Final and initial, after, before. So here we have a point. We want to know what the acceleration is, right? So isn't this V final or V after? Isn't this V before or V initial? Well, yeah. Okay, so just look at this as a V final or V after, and this is a V before or V initial, and do the vector subtraction. So get your piece of paper and pause the video and do the vector subtraction, please. All right, so we're back. You just did this 15 minutes ago, right? And I told you it was important, and I told you we're going to see it again. So there you go. It points towards the center. So again, this is V after. This is V before. So here, I'll do it. So, okay, so we want V after, which is sort of kind of like that. V after. And then This is v after plus minus v before. Okay, this is the vector before, so we want to switch the direction. So it's like this, v before, and then bingo, that's delta v, which is exactly what you did a little while ago. And you know, there's nothing special about point A, right? You could do this at any point you want, and the acceleration vector is always going to point towards the center of the circle. Always. It's always going to point towards the center of the circle. Okay? Always. Oops, you didn't see that? All right? Okay. So, I mean, sorry to say this, but we'll talk about this more later. Right? We'll talk about that much more later. But just remember that. For uniform circular motion, the acceleration vector, wait a second, what's changing here? Just the direction, right? Because the speed is constant. So this acceleration vector, all it does is change the direction. It doesn't change the speed because the speed is constant. So keep that in the back of your head because we will use it later, I promise. All right, new topic. Now we want to talk about two-dimensional motion. All right, now I have to apologize. So typically, I would do a demonstration right now. So here's the demonstration. So this thing, you can't see the whole thing. It's called a projectile launcher. So it just shoots a ball out. All right, so we have one ball that's stationary. It's magnetic, so this thing just holds it with a magnet, right? And then this ball shoots out, and it hits this guy. This guy goes flying, and this ball, when it hits this ball, just goes straight down. Okay? So this ball that got hit goes flying. The ball that was initially moving just falls straight to the floor. Now, the question is, which ball hits the ground first? Now, in order to do this demonstration, I mean, our eyes aren't good enough. What you have to do this on a floor that's tile. And you just listen to what happens. So if the balls hit the floor at the same time, you just hear that one sound. Well, this room is in the library. It has carpet. No way. It just wouldn't work. It wouldn't be loud enough. Sorry. I mean, what can I say? All right? So, but anyway, so yeah, this is what happens, okay? So like I say, this is the ball that's stationary initially. This ball comes out, hits this guy. The moving ball falls. This one, phew. Okay, so what we do when we do this demonstration, this thing has three settings: short range, medium range, or long range. So first we put it on short range, you know. So this ball maybe, you know, just goes to here or something like that. This ball falls, and they hit at the same time. But then we say, okay, let's put it to medium range. So now this ball goes way over here. And guess what? They hit the floor at the same time. Then we say, let's put it to long range. So we really crank that spring, you know? And then, again, this thing just falls, and this thing goes way, you know, over here somewhere. And you listen carefully, and by golly, they both hit the floor at exactly the same time. Now, why is that? Well, you know, after the collision, I mean, as soon as this guy, well, yeah, after the collision or after this ball leaves the projectile launcher, let's just say after the collision, what's the only force acting on the balls? After the collision, what's the only force acting on the balls? Gravity, correct? Now, isn't the acceleration of gravity the same for this guy and this guy? Well, yeah. So don't the times have to be the same? Well, yeah. All right? So that's all it is. It's just free fall, you know? After a collision, the only force is gravity. Okay, now, what we want to do with this thing is we want to consider the horizontal and the vertical components separately. And we're always going to do that, just like we did with those equilibrium problems, all right? Now, think about it. So this guy, it just has a vertical displacement, no x displacement. This guy has the same vertical displacement, but a huge x component, right? So same y, no x, large x. So are those x's and y's related? Not at all. They're completely independent, right? Completely independent. Well, how about the time? Well, obviously the time is the same. So here, this is what I was trying to say. Okay, so here's an American football player kicking the ball. Notice there's a horizontal component and a vertical component. So the horizontal motion and the vertical motion, they are completely independent, although they are connected through the time. Okay? All right, now what's that got to do with anything? You'll see. All right, so when we did one-dimensional motion a while ago, that was one-dimensional motion with constant acceleration. And you learned those three kinematic equations. And I hope you should have them learned by now. So now we're going to do two-dimensional motion with constant acceleration. Now remember, the x motion and the y motion, completely independent. So what do you think we're going to have with the equations? Well, guess what? The same equations, exactly the same, except for subscripts. Well, you'll see. All right, so this is, velocity final x, velocity initial x, ax delta t. Well, we want the y equation. Velocity final y, velocity initial y, ay delta t. So they're the same, right? They're exactly the same, except everywhere here where there's an x, we put a y. So that's why I had to memorize these equations. Because if you know these three, guess what? You know these three also, right? And so there you go. Now you know now you can handle motion in two dimensions. It's just twice this, okay? Now, you might think, oh my gosh, 6 equations. Well, it gets better. It gets better, all right? We're going to talk about a special case. It's called free fall, which we've already talked about. But now we're not going to call it free fall anymore, although if you want to, you can. We're going to call it projectile motion, okay? Projectile motion. So projectile motion, which is nothing but free fall, to tell you the truth. Okay, so if I throw something, that's projectile motion. Now, what's the only acceleration after it leaves my hand? The only acceleration, there's a sub y, which is minus g, right? Which is constant. Now, if I throw something, after it leaves my hand, is there a horizontal acceleration? No, because we're ignoring air, which is okay. So a sub x equals 0. All right, this is awesome. Why is that awesome? Well, think about it. Okay, so projectile motion, a sub y minus g, which is constant, ax is 0. So, this is 0, so goodbye. This is 0, goodbye. This is 0, goodbye. So we have this, and this. Now, does this tell you anything? No. It just says that the final x velocity equals the initial x velocity. Well, no kidding. I mean, remember, there's no acceleration along the x direction. So that means that the velocity along the x direction doesn't change. So no kidding. So this is sort of a waste of time. This is also a waste of time, right? This just says v final x squared equals v initial x squared. No kidding. So do we really need these two? Do they tell us anything new? No. Oh, by the way, I did something else. So everywhere where there's an ay, I put in the minus g. See, minus g, minus g, minus g. Okay, so these two equations are a waste of time. So there. All right, so instead of having 6 equations for projectile motion, which is a special case of this, right? I mean, this is always true. But for projectile motion, where we have this situation, we have our 4 equations. So not so bad. Not so bad. Okay, now, so there you go. All right? So those are the projectile motion equations. Okay, I'm not going to prove it, but I'm going to tell you. So anytime, you can work it out mathematically, but we're not going to do it in Physics 105, okay? Anytime you have a projectile motion problem, so you throw something, So whatever you throw is always going to go in a parabolic trajectory. It's always going to be a parabola. It might be a parabola like this, it might be a parabola like that. It doesn't matter. It's always going to be a parabola. And again, you can show it mathematically. So this is an incredibly important slide. Have you heard that saying, a picture is worth 1,000 words? Well, this is one of these pictures. It's incredibly important. If you understand this picture, you understand projectile motion. It's as simple as that. So let's go over it in gory detail. Okay. All right. So first of all, here's the trajectory. Nice parabola. That's what number one. Okay. Number two, so here's the velocity vectors, right? They point along the parabola, right? Okay. But we don't care. Well, we do care. But we also want to resolve things into x pieces and then y piece. So look. Let's talk about the x. So here's the x velocity of this guy. X velocity, x velocity, x velocity, x velocity, x velocity, x velocity. What do you notice? Do the directions change? No. Do the magnitudes change? No. Why is that? Because ax equals 0, right? Nothing changes along the horizontal direction. So that's number two important thing, right? Number one, parabola. Number two, because ax is 0, these vx vectors are always exactly the same. Same direction, same magnitude. Now, ay equals minus g. So if you throw something up, it's going to get slower, 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 then turns around faster, faster, faster. So look, here's v initial y, kind of fast, slows down. What's vy here? 0, right? If you throw something up, it stops, then it turns around. So vy is 0 here. All we have is the x component. Then it turns around. So here's vy, and right? Here it is again. It gets faster, faster. So that's the third important thing. Now, let's talk about symmetry. We talked about this before. Notice that this vy, just the magnitude, equals this vy. In other words, this speed equals this speed. Or you can say this velocity is opposite to this velocity. This speed here, again, we're drawing a horizontal line, right? Draw a horizontal line. So this speed equals that speed. Remember we talked about that before, the symmetries? So there you go, right? All sorts of cool things with this one particular slide. All right, let's have you answer some questions now. You are holding a rifle pointed parallel to the ground, or to the earth, whatever. You drop a bullet, and you fire the rifle at the same time. Which bullet hits the ground first? Ignore air resistance and assume that the earth is flat. So we're members of the Flat Earth Society, right? Okay, so pause your video and figure it out. All right, we're back. So this is the demonstration we did, right? We didn't do it with a rifle. We did it with a projectile launcher, right? As soon as the bullets leave the gun, it's free fall. And free fall has the same acceleration due to gravity. So the time to reach the ground is going to be the same. They both hit the ground at the same time. Okay? One more. Oh, this is a great one. Hold on. By the way, this last one, Mythbusters has I think they have a show where they show this. It's kind of a neat thing. Okay, let's do this one. So here's the ground. Here's a cliff. All right, a person standing at the edge of a cliff throws one ball straight up and another ball straight down with the same initial speed. Just pretend it's the same, okay? V0, V0. All right, so they both have the same initial speed. neglecting air resistance, the ball to hit the ground below the cliff with a greater speed is which one? So in other words, this one just goes straight, right? This one goes woo, and then phew. Okay, so pause your video and figure it out. Okay, let's talk about it. This is all about symmetry. So this guy is going to go straight up. So, so it's going to go straight up, stop, and then turn around. So I'm going to draw when it turns around here. Now, whatever. Okay, this thing had initial speed v0. So what's going to be the speed right here? v0. So it's going to be exactly the same speed as this guy. So therefore, when they hit, they're going to hit at different times, obviously, but when they hit the ground, what's going to be true about their speeds? They're going to be exactly the same, exactly the same. All right. Okay. All right, so earlier, okay, this guy. All right, so just pretend we did this demonstration, right? And so, again, this was perfectly horizontal. I don't know if I said that before, but I should have. This was perfectly horizontal. So this ball here initially was moving perfectly horizontally, all right? So what did we learn from this? We learned that the time in the air was exactly the same, all right? So there's a fancy word for that. Time of flight, okay? It's just how much time it was in the air, that's all. So what we learned here, again, was that the time of flight is the same. So what we want to do is we want to prove it. So I want to show you how to do this because you're going to do it in a future lab. So pay attention, right? Okay. So what we want to do is we want to prove that the time of flight is the same. So when the vertical component of the velocity is 0, right? This ball only has a horizontal component. It doesn't have a vertical component. So we want to show that the time of flight is the same when this is true. So it's the same if the v0y is 0, okay? Now, typically, when you're asked to prove something like this, this is kinematics, right? Time, velocity, acceleration. So it's kinematics. So you want to look at one of your 3 kinematic equations. So let's do that. Ooh, right there. Okay, right? This is free fall. So we want to look over, we want to look over here. Now, we want to do something with time, right? We want to do something with time. So this is not going to help us. So it's either this one or this one. Now, let's see. We don't really know much about the velocities, So we really want to use this one, okay? All right, let's do it. So the second one, y final equals y initial plus v initial y delta t minus 1/2 g delta t squared. All right, now, now we already said v, okay, so this is v initial y, this is v initial y, who cares how you do it, right? How you label it. But this is 0, so goodbye. And let's make it simple. So let's subtract this. Let's subtract y initial. Let's put it on the other side. So we have y final minus y initial. Okay. Now what is that? What's y final? What's y final minus y initial? It's delta y. All right, delta y. So let's just save time. So now, what are we going to have now? We're going to have delta y equals minus 1/2 g delta t squared. Now what are we trying to find? We're trying to find delta t. So multiply by 2, divide by g, so we have minus 2 delta y over g equals delta t square root. Right? Now, agree? That's just good old math, right? Now, some people will look at that and they'll freak because they see a minus sign underneath the square root. Why freak? What's delta y? delta y, remember, it went from here, it went from the projectile launcher to the floor, right? So the floor, we're going to call y equals 0. We can call this y equals, I don't know, let's say a meter. So what's delta y? It's y final minus y initial. So it's going to be 0 minus 1 meter. In other words, it's going to be negative, right? It's going to be negative. So all I'm saying is delta y is negative. So this negative kills that negative, so you get a positive. All right, anyway, look at this. Look at this. Look at this. What does delta t depend on? All it depends on is the height, right? The height of the projectile launcher. Okay, so the time it takes the ball to hit the ground only depends on this height, and of course, g, but no kidding, right? So it does not depend on the initial speed, right? It does not depend on Vx initial. All it depends on is the height. So like in your lab, when you're told to prove something, this is how you do it. You start with a kinematic equation. You do whatever you have to do, and you solve for whatever you have to solve for, right? So we just proved that the time of flight only depends on delta y. It does not depend on Vx initial. Okay? That's all. All right, that's a good place to stop. Let's stop.